assignment 4, as well as the write-up that's going to go with this portion. So we're going to be doing write-ups as much as possible in conjunction with our Excel assignments now, um, because this is a very important part of the process of research, okay? You have to report your findings. So we want to know what these are saying to us, what all the statistics mean. So we have an online class of 22 college students who began the semester taking a pretest that was created by their instructor. Now, after completion of this course, a post-test was administered. So our question is, did the course impact student learning? Now, our null hypothesis would say there's no difference between pretest and post-test scores. But if the students learn something, then their post-test scores should be higher than their pretest scores. That is our research hypothesis. We are predicting a one direction because we would not expect that the course would make them forget information they already knew, right? So we're only predicting in a one-tail hypothesis that the post-test scores will be higher than the pre-test scores. We have um, we have a good reason to predict a one-tail hypothesis, right? So first things first, we need to think, okay, what type of test are we doing? Well, because it is the person taking the pretest and the same person taking the post-test, we're not comparing two separate groups. We are comparing the person to themselves. They just took the test and then they took the post-test, right? They took the pretest, then the post-test. So this is a within subjects design, right? Because this is the same person and this is the same person and so on. So we need to think of what assumptions we're going to have for this paired samples t-test is what we're going to use. So for the paired samples t-test, we need to know, are the variables in the data continuous? Well, we have, these are percentages, right? They go up to 100%. This is going to be a good continuous variable. They could have like 61.25%. They could have a 46.4%. I kept it a little bit more simple by just putting whole numbers here, but they can have the decimals also. So yes, these are going to be continuous variables. There's no way to, you don't need to run anything to check that. That's more of like, I've observed this, right? So we also look at the dependent variable should not contain any outliers, all right? So I'm going to look at both of these for outliers. Now this is something we're going to need. We don't need to check it for outliers or anything like that, but it is just the difference between these two. So I just took this minus that equals that. You could do it the other way. It doesn't really matter which one you're subtracting because it's going to mathematically come out the way it should, as long as you've done it properly. But this is just subtracting these two, okay? But I'm going to check these two for outliers. So we're going to select all of the data that we want to create a box plot for. Box plots are going to check for outliers, right? So we're going to say insert, and we find the box plot under the histograms here. Box plot. Okay, so I don't have any outliers. This is going to, I'm going to change this to box plot for outliers. So I know exactly what I'm using this for, right? I'm going to keep that up here to try to keep my work nice and neat. Now, an outlier would show as a little X somewhere up above or below these. So this is pre-test, this is post-test. There's no outliers. We don't have to worry about that. So yes, that assumption has not been violated. Neither one of these have been violated. So we can move on to the third assumption. This is that the dependent variable should be normally distributed. Now we are going to go ahead and check all variables here for normal distribution. Um, Now I recommend starting first with filling out this table. Now there is a way that you can get more descriptive statistics under the data tab, but right now I'm going to focus on just a few of these because you don't need all the other stuff right now for this assignment. Um, but all I have to do to check is I've got this already created for you guys. You just need to fill it out. So what is the skew of pretest? So all I do is I find this function and I'm going to select what data that I'm asking it to check the skew on, and it will pop up the skew. Now, if it popped up something with more decimals, that would be something I'd have to fix because you want it to 2 decimal places. But for me, this popped up this way, probably because I've messed around with it already quite a bit, so it has information already stored in there. But I'll show you how to do the decimals on another thing. So I'm going to also get kurtosis, and then mean, so we go to average, and standard deviation. Now, one of the questions that I got before was standard deviation. What is the difference between all these functions? When do we use them? So if you're like me and you have this particular one, all this one is this one as well. So I just usually use that, but for the sake of keeping things more understandable, I'm going to explain the difference between these two. This one is for samples. So um, because I'm taking the information that I'm using here and I'm going to think, okay, so if this course has impacted learning once it's over, then I'm going to expect that to have impacted learning in all subsequent uses of the course. Versus if I just wanted to focus on this one course and I was planning on creating a new course for the next group, right? So that's a sample. So S stands for sample, and I'm using this course or these students as a sample to help me understand how to use this course in the future. So I would use this. Now, if I had a population, I would use this one. Now, you're going to have populations sometimes in research, but very seldomly do you have population data. So almost always we're going to use this. In this course, I'm going to only use samples unless I specifically say population. You will always expect that to be a sample, okay? So we're going to click that, and I am selecting data again, right? And it's going to pop up what it needs to, and I'm going to do the same thing for each of these on the post test. So I'm going to do this really quickly without too much chatter. And now for the differences, I don't really need these on the differences. I do need this for calculating the effect size though. So I'm going to get the average of the differences and the standard deviation of the differences. Okay, So I have that completely filled out now. But we're still in this assumption, are the variables normally distributed? So for skew and kurtosis, as long as the numbers are between +and -2, so anywhere within that range of numbers, negative is the -2 to +2, anywhere in there, then you don't really have any problems with skew and kurtosis that we need to even consider, right? And we're not going to have a whole lot of that in this course anyway, because there's a whole lot of extra stuff that you have to do if you have problems with normality. They're called transformations, but we're not worried about that in this course as much. So I'm going to keep um, I just want you guys to know, if you have skew and kurtosis issues, you can find them generally here. You can also look at um, the distributions. So histograms will give me the distribution of each of these. So I've got this. I'm going to label this properly. And post test. Okay, label that properly. It's important to keep labels on there, just so you don't get confused about what you even use that distribution for, okay? So that's very important to reporting statistics, is to make sure you've labeled everything. Now, I don't like these distributions, and I think it does a better job in other statistical software to show these, because these are called bins. So the way it has binned really impacts if it looks normal. But I would say that these aren't giving me like very definite violations of a normal distribution. The sample's small, so it I wouldn't trust these necessarily. This looks fine. This one looks like it could end up in a skew, but I am not going to worry about that because these numbers are showing me that it seems to be fine. So I do want to still look at the distributions, but you use these things together. So it's really important that you look at both. But for me, this looks fine. I would say there's no violations of normality for this set of data. So because I have met my assumptions, no violations, I can move on. So I will be performing the paired sample skew test. And to do that, I am going to go to the data tab. Now I'll go to data analysis. And then there's a whole list of things you can do here. Like here is descriptive statistics if I wanted to get those. But it gives you a whole lot more than I usually ask for. Um, but you can mess around and look in, see how that shows up for you. But for this, we're just going to go to the paired two sample for means t-test. And it's going to give us the, and I've already done this, so it's going to give me the output that or the ranges and everything that I already wanted. It will pop up alpha already, and it will give you the 0.05. Leave that there. That is the standard, so just leave it as is, and all you have to do is put in your variable ranges, and your output, where you want your output to be. You can do a new workbook, but you would have to copy and paste it into this sheet for us because this is how we're going to grade them. But the variable one, I've already clicked to keep the labels, so I'm going to include the label here. If you do not include the label, if the label is not checked and you're not including it, you need to not select it in your range. Because if you do select, if you don't select it and you do put that you have selected it here, it's going to expect this top row to be the label. So it's going to mess your statistics up. So I'm going to also do post test. So there's my selection, and that's where I'm gonna put it. And when I click OK, pops up my table here. So because this is APA format, we have to focus on the decimal points, right? Because you have to have 2 decimal points for APA format. So anything that's a decimal, we're going to make into 2 decimal places. We're not going to use all of these, but I still want to be in the practice of using decimal places. Now, one thing this does that I think is very beneficial, because not all of us understand scientific notation. So if you are a person that does not cannot read this, then this is going to be very beneficial for you to do. But you need to select everything, and then once you click it once, it changes everything to normal decimal anyway. So your p-values, which we kept one tail, so you really don't need this down here, but again, get into a good habit of doing it anyway. P-values, you can do that to 3 decimal places because in this instance, because you need to. Okay, so this says it's 0. We know it's not. Like, this is the actual number. Same thing with this. This is the actual number. This is not 0. But that's how it shows up because of the way the decimals work. And that's why scientific notation is used, because it starts here. And they can tell you how many zeros to put in front of it. But for us, we're just going to look at this here. The p-value here is p is less than 0.001. Because it is, for one, it is less than 0.001. 0.001 will be here. There's where the 1 would be. So it is less than that, but it's not 0. And you can't put 0. There's no p-value that's going to be 0. There's always going to be that margin of error. Okay, so you have to put is p is less than 0.001 or something that shows up like this. Now it might show up as 0.05 or 0.04, whatever. So that can be to 2 decimal places. That's fine. You do have to make sure if it's like 0.051 that you recognize that this is greater than 0.05. So you do have to be careful. But again, for this particular assignment, make sure these are the 3 decimal places. I believe in your other data set is going to show up that way anyway. You're going to need to keep it to 3 decimal places. But for pull this out of the way again. Sorry, I have a very small screen for my laptop. So in a minute, I'm going to show you how to use this information to fill this out. Okay, all this information. But now that I've found a difference here. I found this is statistically significant. So I have to check the effect size. So I definitely know there's a difference, or my my sample, statistically significant um, is the difference between the means. So the difference between the means here is statistically significant, meaning so there could be some issues. There might be there's a chance that this is wrong, but it's a very low chance. Um, One tail, this is very low chance that this is incorrect, but there is always going to be a chance. So you still have to keep that in mind. But we're going to look at effect size. So the first thing we need to do is move over the means. First, you need the mean of pretest. So pretest mean is here. It's also here, but I'm not worried about that. Post-test mean. Now, this is the absolute value of the mean of the differences between the two groups. So the differences, the mean is negative 20.86. So here, I'm just going to put 20.86 because we can't have a negative effect size. So the effect size is going to be positive. This is going to, we're going to need the absolute value. Now here, this for Cohen's d, you need to take this number and divide it by the standard deviation of the differences. So we're going to take this number and put a slash for division, and then we're going to select the standard deviation of the differences, and it's going to pop us up what the effect size is. So that's when we think about our measurement of Cohen's d. 0.2 is small, 0.5 is moderate, and 0.8 is large. So this is a very large effect size comparatively, right? So we need to make sure that not only do we report that number, but we have to report what that number is telling us. So when I go to write this up, I have to make sure I'm telling the reader what kind of test there was. So we have a paired samples t-test that was conducted to test our hypothesis, and we need to put that in here, to test the hypothesis that post-test scores were higher than pre-test scores. Now, we need to go ahead and report if the assumptions were violated. So the variables were continuous, indicating no violation of assumptions. Each variable was examined for outliers. You can put, using a box plot, but none were found, indicating no assumption violation. Now, distributions of each variable and skewness and kurtosis, so the skewness, kurtosis, as well as the distributions of each variable were examined for the assumption of normality. I'm sorry if you can hear I have a pug puppy, so I'm sorry if you can hear him snoring, but he's snoring right now. But I have these things to tell me that there's no assumption violation here. So since there's no assumption violation, we need to report the numbers here. So pretest, these are the skew and kurtosis for pretest, the skew and kurtosis for post-test, and the indication that it's between these. These are the numbers that I'm using. So there's no issues with normality, thus no assumption violation. Now, since I have those steps reported, I need to go ahead and report the findings for the t-test. So we have the scores for the pretest. These are the means and standard deviations. So I need to give those descriptives about the variables. So scores for the pretest um, are mean and standard deviation, and then scores for the were lower than scores for the post-test. So post-test is the mean standard deviation here. And this difference was statistically significant. Now the way we write this is we have our t, and then we have our degrees of freedom. So we have 22 people. We subtract 1 degree of freedom, and the degrees of freedom will be given to you on your report as well. So you can put t of this number equals, and then you put what the t-stat was. And this one is negative 4.88. And then you put the p-value. So p is less than 0.001 because, like I said, we cannot report 0.000. It's p is less than 0.001. And then we report the effect size, which is 1.04. So t of 21 degrees of freedom is negative 4.88. The p-value is less than 0.001, and the effect size is 1.04. The effect size was very large. Therefore, we reject the null hypothesis. So that's really important wording there. You reject the null. The null is that there's no difference in scores between pretest and post-test. So we're rejecting that. Okay, we're rejecting the null hypothesis that there was no difference between the pretest and post-test scores because our evidence supports the research hypothesis. The research hypothesis is that post-test scores are higher than pretest scores. So that is basically saying, okay, we have these two groups, and the two groups are where they took the pretest, they took the post-test. We're testing the difference in means. Is this mean higher than that mean? So is it statistically significant? Because we can have a ton of error. So we need to check based on our sample size, which is pretty small. Do we still have a difference based on sample size, the variation within them, everything else that you've got, all these indicators, are these different? And yes, they're different. The effect was large, and so we can reject the null that nothing's happening and say basically something is happening. The post-test scores are higher than the pre-test scores. Now, once you have that written out, and I did give you guys this example write up so you can kind of use it as a guide. But once you have this written out, you are done. So you have these items. So you should have, once you're finished with your assignment, you should have a box plot for outliers. You should have two distributions, one for each of these two variables. You should have the descriptive statistics of mean and standard deviation, as well as checking for normality with skew and kurtosis. All this should be filled out. You will have a table here for the t-test that, although you don't need all of this because you didn't do a two-tail, you did a one-tail. So that's where you look. And you don't really need to worry about this right now. We haven't even learned this. But you can look at this. It should have the decimal points that should be to 2 decimal places, to 2 decimal places, and it should have the p-values to 3 decimal places for this particular assignment. So then once you're done, you have this effect size box. This should all be filled out. And then for the write-up, you will have to write this, or write your null hypothesis and your research hypothesis. You don't need to do anything here, but you are welcome to write something in if it helps you remember. But this is not something that I'm putting on a rubric to grade or anything like that. So you don't need to have anything written there because you are going to mention it here. So you have to have it mentioned within this paragraph. Everything I have in here is necessary for you to have, um, based on the numbers that you get. So you will need to make sure that you're attending to each of these separate concepts within here. But that is it. That is what you would submit. Um, it it can look just like this as far as like the layout. That doesn't matter to me. I just want to make sure that you understand what you found, that you have all these items within your Excel file, and um, that you understand what this means. If you are struggling with that, please reach out. I will also try to create um, a couple more videos for you guys. So I hope this helped. And just remember, you do want to submit, then wait until you get feedback to submit again. If something doesn't show up, we'll let you know, but you aren't going to lose points for that. So you will be able to earn your points back, but you get a resubmission. And please do not submit without getting your feedback first. Okay? So I hope this helped, and good luck, guys.